Okay, so thanks everybody for coming. Um, Today we have Shaily Rahman, and I'm actually going to let Alan do the introduction. So why don't you get started, Alan?
Okay, well, it's a pleasure to introduce today's speaker, Shaily Rahman, who is a postdoc here in my lab. Shaily has spent her life in various corners of the world, but academically started off with a bachelor's in chemistry, minor in math from McGill University. Continued there, getting a master's degree in Earth and Planetary Science, working with Al Mucci and Bjorn Sundby, who not only is a great geochemist, but my experience is he's one of the nicest people around.
I concur.
Shaily then worked as an environmental scientist and consultant for a few years before returning to academia and got her PhD in chemical oceanography from SUNY Stony Brook. Her advisors were Bob Aller and Kirk Cochran, which, it's not quite like being, in physics and having Einstein and Feynman being your advisors, but those are two pretty darn high profile people. She's got a great background, did a postdoc at Florida for a little while, and then has been here for about a year. She's published, it's over a dozen papers. Some are, still in review. And she's got a couple more in progress, including a couple from her work here. She's won various awards, teaching fellow, a scholarship. She was selected to go to disco, which has nothing to do with dancing. I keep trying to figure out some superlative descriptor for Shaily. And the reason for this is that as a PhD student, she was measuring cosmogenic silicon-32. Now, it's estimated that there is less than a kilogram of silicon-32 on Earth. So that ain't much. And just doing a back of the envelope calculation, if all of that were dissolved in the ocean, the dissolved concentration would be in the zeptomolar range. So maybe we'll call you Madam Zepto or something.
Halloween costume.
But without further ado, let's listen to Shaily.
Okay, let's see if I can get this to work. All right, you can see my screen? Okay. And can you hear me? Okay.
Yeah.
Thumbs up. Okay, great. So I'm going to be talking to you about the marine sedimentary silica cycle, which is a favorite topic of mine. And I'm going to be talking specifically about reverse weathering reactions and the importance of the coastal zone. So most of this work was done at Stony Brook University. And there is a group in France, the Biomengo group, who helped with logistics of getting out to French Guiana and collecting supplies. And they are working in these mangrove systems that are along the coast of the Amazon Guyana's dispersal system. And the study was funded by NSF. So let me start out by defining what reverse weathering is. So silicate minerals are weathered on land through the formation of carbonic acid. And this process will release dissolved silicon, major cations, along with trace elements that may be hosted in that silicate mineral And it also releases bicarbonate ion or alkalinity. And this process is one of several reactions that have been proposed to stabilize the temperature of Earth's surface over geological timescales. Some other reactions which also control atmospheric CO2 over long timescales are volcanic outgassing and tectonic uplift. And recently, in the last few years, reverse weathering has enjoyed this revival of yet another mechanism that can moderate or modulate or modify, not sure yet what it does exactly, the atmospheric CO2 concentrations and the coupling between the atmosphere and ocean. So the questions that reverse weathering initially, the impetus for describing these reactions, some of the impetus was just this general question of, okay, so if you're supplying all of these cations to the ocean and all of this alkalinity, why don't we have runaway soda lake type oceans? Because calcium carbonate, the sink for calcium carbonate, isn't enough to close the alkalinity budget in the ocean. And the other question is, what are the sinks for these major cations in the ocean? For example, there's been little change in the seawater dissolved potassium record over the last 600 million years. And so even though magnesium and calcium may go into a calcium carbonate, potassium won't. So reverse weathering reactions were formally defined by Mackenzie and Garrels in 1966. And this describes, this is a general reaction, it's not balanced, and it describes the formation of a new clay phase at the sediment water interface. And these reactions take up dissolved silica, dissolved metals, cations, other trace elements, and it also consumes alkalinity and produces CO2. So you're taking all of these dissolved fractions at the sediment water interface, and you're producing this new amorphous aluminous silicate phase initially that then matures and will become a clay. Excuse me. So I'm going to give you the conclusions of my research straight away, and then go into the canonical model of the silica cycle, how I use silicon-32 to quantify reverse weathering reactions in continental margins, and how those reactions fit in this global silica model. I won't have time to talk about the links to potassium uptake or germanium uptake or other trace metal uptake, but I can at a later time. Instead, I'll just focus really quickly on how reverse weathering reactions modify the conceptual linkages between the marine silica and the marine carbon cycle. And then I'll close with summary revisions and give you the conclusions of my talk. So if you're sitting around having a cup of whatever and you're wondering what was Shaily talking about, here's a nifty acronym to help you remember the major conclusions of my talk. Maybe you're wondering how the silica and carbon cycle are coupled, or benthic pelagic coupling. So reverse weathering reactions exert critical controls on the marine carbon cycle. They happen rapidly, in less than 1 to 2 years. They seem to be forming ubiquitously in continental margin sediments, so in temperate zones, subtropical and tropical zones. And now there's emerging evidence that they're actually happening in Arctic margin and Antarctic margin sediment. The magnitude is large. It's significant enough to potentially balance other mass budgets where there's this unknown sink of lithium or germanium. Reverse weathering reactions have been proposed to balance those budgets, though we still are lacking all of the supporting evidence where you've actually gone out and found, high association of germanium or lithium with an oncogenic clay. As I mentioned, reverse weathering has enjoyed this recent revival in modern mass budgets. It's been proposed to balance the germanium isotope budget, rare earth element budgets, and also potassium budget. And generally, silicon-32 can be a really effective tracer and important tracer in ocean processes. It's just that we have so few measurements of silicon-32 in the ocean. I think the geosex transects were the cruises that that had any measurements of silicon-32, and they measured about 100 discrete samples throughout the world's ocean. And reverse weathering has also enjoyed this reconstructions. So the magnitude of the sink and differences in the magnitude of the sink through time has been used to potentially explain the lithium isotope history of Cenozoic seawater. Now, lithium isotopes are tracers of terrestrial weathering and weathering congruency. Magnesium isotopes have also been used to describe seawater, ocean cooling, and surface temperatures, and reverse weathering reactions are a potential sink for magnesium. And in longer time scales, they've been modeled. The Precambrian silicon isotope mass balance has been modeled, and as well as a coupled silicon carbon model over the last 4 to 5 billion years, excuse me. And reverse weathering, because it produces CO2, is maybe a potential explanation for warmer surface temperatures. So, but in modern coupled cycles, this is a very complicated, initially very complicated seeming one. It's often missing from modern coupled models. Now, modern coupled cycles. So this is something from McKenzie and Anderson 2013. This is the same Fred McKenzie who, of McKenzie and Garrell's 1966, postulated this general reverse weathering reaction. And you can see that in the coastal zone, which is the zone that I'm going to be talking about, carbon, nitrogen, phosphorus, those linkages are explicitly modeled, but silicon isn't. And this is that climate reconstruction study that I talked about over the last 4 billion years. And these climate reconstructions have missed recent modern silica budget updates, which are usually the starting point. This is 0, time equals 0 at present day. They've missed recent budget updates or rate constraints, and they use this presumed or assumed DSI consumption to alkalinity consumption molar ratio, or you can think of it as your DSI consumption to CO2 production ratio. So here's reverse weathering. This is, I would want to just point this out really quickly. So this is your magnitude of your reverse weathering sink, and this is one of the things that they model, which is your atmospheric CO2. So this is atmospheric CO2 with reverse weathering and with no reverse weathering. Again, using these presumed silicon to alkalinity ratios, rate constants, and these older budgets. So what is the one of the most recent budgets of the marine silica cycle? This is a synthesis that was done by Paul Traeger and Cristina de la Rocha in 2013. And in the synthesis, these are the major inputs of dissolved silica to the ocean. You can see that rivers dominate. All the units are in teramoles per year, and a teramole is 10 to the 12th moles of silica. Dissolved rivers supply about 6 teramoles. Low temperature basalt weathering or marine silicate weathering supplies another 2 teramoles. ASI, this is amorphous silica like phytoliths or aluminosilicate or gel-like silica phases that can form on the surface of particles that will dissolve very rapidly when they encounter a salinity gradient, like in the estuary. So this will likely dissolve in a day or two once it enters or exits the river mouth. So this is part of the DSI supply. And you can see that some marine groundwater discharge, dust, and hydrothermal vent inputs are assumed to play a minor role. The inventory is about 100,000 teramoles, and the residence time is about 10,000 years. So once it's in the ocean, the marine silica and carbon cycles are again coupled through silicifiers, mainly diatoms. Silicifiers precipitate biogenic opal, this amorphous SiO2 phase. And because glass is heavier than water, it acts as a ballast mineral. And it's a significant fraction of the biological portion of the carbon pump. Export production. And export production sequesters organic carbon from the surface ocean to deep ocean sediment. Now, what is the fate of this biogenic opal that's deposited in sediment? So in the canonical model, this 2013, 1995, all of these models, when you first deliver this initial biogenic opal pool to sediment, in the canonical model, the presumed pathways of how this biogenic opal pool behaves is that it'll either dissolve and diffuse back up into the water column, or it'll get buried as an unaltered biogenic opal phase. But there is now I think, a preponderance of evidence that shows that this initial pool of biogenic silica that's delivered to sediment undergoes rapid diagenetic alteration. And I'm going to call that pool BSI altered, which is right here. And two major alteration processes that it can go through is that it can be associated with metal oxides. So iron, dissolved iron, manganese, and aluminum can either absorb or precipitate on biogenic opal frustules. And the other alteration pathway or diagenesis pathway that it can take is that it can form an ophthalmogenic clay. And the formation of an ophthalmogenic clay will, to remind you, will take up dissolved metals, alkalinity, trace elements from pore waters and the overlying seawater to form this amorphous aluminosilicate phase. And I'll refer to BSI clay as the end product of that diagenetic pathway. I want to mention that tropical rivers supply more than 50% of this riverine DSI input. So in this canonical model, the major modes of burial are either opal burial in shelves and opal burial in oceans. And I want to mention that the opal burial in shelves is actually based on a presumed carbon burial with a presumed silicon to carbon molar ratio of 0.4 to 1.2. And in this model, you can see that reverse weathering reactions only constitute a minor fraction of that sink. They're presumed to form very, very slowly. And they are occurring somewhere on continental margins, but the precise geographic locations or general provinces or regions are unknown. And if you've done your math, you can see that the total inputs of dissolved silica to the ocean is about 11 teramoles per year in this model, and the outputs are about 7 to 8 teramoles per year. So you've got this missing sink of silica of about 3 to 4 teramoles per year. So as you know from the title of my talk and from my conclusions that I've already given you, could this be a bigger reverse weathering sink? That's the question that one of the questions that I'm going to ask. And the reason for thinking that there may be a larger reverse weathering sink than the 5 to 10% of total DSI inputs that it's assumed to sequester is that there are numerous lines of evidence that point to rapid ophthalmogenic clay formation. You've got field observations where you have anomalously low dissolved pore water silica concentrations, much lower than what you would expect from the dissolution of biogenic silica. You have incubation studies where you see silica substrates that are rapidly converted to clay in less than a year. You've got pore water profiles that show uptake of silicon and major cations, anions, trace elements. And even just from regional silica mass balances, a lot of this is in the East China Sea, where you're really tracking riverine inputs, outputs through ocean currents and primary productivity, you can see that there is quite a lot of storage of this marine biogenic silica that's produced in continental margins in sediment. And very exciting, there's now a lot of, starting to be some promising evidence from stable silicon and germanium isotope compositions of pore water and solid phases. And as you saw before in some of my snapshots of paper titles, potassium, magnesium are also potential indicators of the isotopic compositions in pore water of a active reaction that may be happening at the sediment water interface. So I want to know, what is the magnitude of the reverse weathering sink? How fast is it forming? And once I know that, how can I couple the silica and carbon cycles more accurately? Now, so I mentioned that there are about maybe 100 discrete water column measurements of dissolved silica through the global ocean. There are only about 10 or 15, maybe maximum, silicon-32 measurements in marine sediment. And those are the older studies are denoted by these diamonds here, and they're all in deep waters. Well, except this one, this is on the slope, but it's still at something like 2,000 meters in the Bay of Bengal. Studies are from the proximal coastal zone, so they're in less than 50 meters of water depth. And I picked these studies, if you remember, tropical rivers supply more than 50% of the dissolved silica to the ocean, so that these sites were characteristic of at least 10 to 15% of the dissolved silica load, as well as being characteristic of 10 to 15% of the total terrestrial sediment yield to the ocean. And I'll be presenting some data from the Amazon River, French Guiana, Papua New Guinea. The Gulf of Papua was a study site, as well as the Mississippi Delta and Long Island Sound. So I want to talk about tropical end members because they play an outsized role in reverse weathering reactions. And one of my favorites is the Amazon Guiana's dispersal system. So the Amazon supplies about 1 billion tons of sediment annually to the ocean. And about 15 to 20% of this outfall moves up the coast from the Amazon River to the Orinoco Delta. And they are transported as a series of mobile mud waves by the North Brazil Current, waves, and tidal action. And they travel up the coast at a rate of 1 to 3 kilometers per year. And most of this mud in this zone comes from the Amazon River. It's like 95% of it comes from the Amazon River. So you can almost think of this as a core. This is the top of the core. This is the bottom of the core. And if you sample along this mobile mud dispersal system, then you're sampling at different depths or different times of that core. So there are a series of 20 to 25 mobile mud waves that are always moving from the Amazon to the Orinoco. And this is a depiction of one of these mud waves. They're about 10 to 60 kilometers long. They extend 30 to 40 kilometers offshore. They're 4 to 5 meters thick, and they're anywhere from, I'm not sure, 5 to 7 gigatons of material in one of these individual mud waves. And they have different geomorphic features. They're eroded, on this side, and it really is like a wave. It's eroded, and this is the depositional edge. You've got intertidal algal flats and mangroves. So one of the most striking, convincing pieces of evidence of authogenic clay formation, or rapid authogenic clay formation in deltaic sediments, are just direct imaging of diatom frustule. So this is an altered diatom frustule. And you can see from imaging that you form these cation and metal-rich aluminosilicate phases on the surface of this diatom. Here are your cations. This is aluminum. This is silicon. And here I've written that, shortened that reverse weathering reaction, just so you remember that you're taking dissolved silicon, metals, major and trace cations, alkalinity, and you're forming this new aluminosilicate phase and releasing CO2. Another really compelling piece of evidence for the rapid formation of an aluminosilicate phase is from incubation. Incubations, and so this is a diatom that's been incubated in topset sediment from the Gulf of Papua. So this is the unaltered phase. So you can see all of how clear and sharp the features are on the surface of this diatom, and then within 6 months, you see the formation of these flaky aluminosilicate, amorphous aluminosilicate clay phases. And these are zoomed in pictures of this surface. Now, tropical deltaic systems behave differently from a steady state one-dimensional system. This is how I was first taught about sediment diagenesis, is to model it as a 1D system, which is what you might do maybe in a temperate estuary. Or this is what you assume is happening in the deep ocean, where you have steady accumulation. And if you go deeper down in the core, this part is older than that part, and you can get an accumulation rate and estimate how old this portion is from that portion. But tropical deltaic deposition systems behave as non-steady state systems, and they have mass movement in 3 dimensions. So in the Amazon Guyanus dispersal system, and even actually along the dispersal system of the Mississippi Delta, you have a formation of these fluid mobile muds overlying more compact relic sediment. Or you have colonizing mangroves that will be sediment traps. And you have quite a lot of formation of algal mats. If you're on an erosional edge, you can scour 1 to 2 meters of sediment very, very rapidly. You can have deposition events that will deposit anywhere from 10 centimeters to 2 meters of mud within a day or two. And you have these evaporative fans. I didn't really sample any sand cheniers, but you also have permeable sediment that can overlie relic sediment. So this is in quite sharp contrast to this one-dimensional system. And French Guiana, if you're looking at it from a side view, it looks like a cliniform delta. And this sediment transport in 3 dimensions, I think, maintains what I'm going to call like these Goldilocks conditions. We talk about these Goldilocks planets for, finding life. Well, I think that these are Goldilocks conditions for reactors for forming these aluminosilicate phases. So you have shore parallel transport. So this is like if you're going into and out of the page with net transport 1 to 3 kilometers per year towards the Orinoco Delta, say. You also have shore perpendicular transport of sediment this way. And you can have deposition of 2 meters of sediment in any of these zones. So you have mass movement in this direction. So this is really a dynamic, physically reworked system. Now, we could not get any pictures of the study sites that I had in French Guiana, but it's hard to get pictures. There's so many clouds around. But this is from a different paper. And most of my samples are from this colonizing mangrove island. These are sediment traps. Usually this region will fill in for about 50 years, and then you'll have a connection from the mangroves to the shore until you get to the erosional edge of that mud wave, and then this whole feature will be gone. And I have had a bunch of cores from these mobile mud belts out here. So what are some of these Goldilocks conditions? Well, this is an image of one of those mud waves. And I'm going to be presenting some some of these Goldilocks conditions from these cores. And the first is that, well, the top 1 to 2 meters is physically reworked, which you can see by the homogeneous lead 210 activity down past 1 meter of some of these sites. And this is very typical of this mobile mud region right here. Now, if you remember from that canonical conceptual model of the marine sedimentary silica cycle, the 2 major modes of alteration that it takes is that it's either dissolves and diffuses back into the water column, or it's buried as an altered clay. Well, if your biogenic silica is dissolving, your pore concentrations are expected to reach or asymptote at about 1,000 to 1,200 micromolar. And in French Guiana sediments, you see that you are far from predicted solubility. You also see potassium uptake in this fluid layer. On top of that, you have these extended zones of dissolved metals. You can see how high dissolved iron can get in some of these cores. I have other profiles that reach up to 1 millimolar of iron. And at the same time, you have limited sulfate reduction. So you have this suboxic zone of limited sulfate reduction, persistent dissolved metal supply. You have dissolved silica profiles that are not reaching the concentrations that you would expect if it was only dissolving. So this is either a dissolution precipitation reaction, or you've already altered that biogenic opal phase. And you also see uptake of potassium. The other thing that I want to point out with these dispersal systems is because they're so close to land, a lot of times you may think that, okay, the matter there should be dominated by terrestrial inputs. It should all be terrigenous. So if you only looked at the bulk sediment composition of organic carbon, it is dominated by a terrestrial signature. It is that dumb, but that organic matter, by the time it reaches French Guiana, is not very reactive. So the organic carbon loading starts out at about 0.7 milligrams carbon per meter squared, and by the time it reaches French Guiana, most of it has already reacted. Instead, when you take a closer look at pore waters, the del C13 and cap C14 signatures are all marine. So you start mixing in marine organic carbon right at the Amazon river mouth or the Amazon Delta. And by the time you get to French Guiana, the organic matter that is respiring or being remineralized is all organic, marine organic carbon. And these mud waves are dominated by marine diatom species that are brought in by the open ocean. So Goldilocks conditions, I'm going to summarize them very quickly. You have a steady supply of reactive marine organic matter, rapidly incinerated. You have an extended zone of suboxia, where you have a lot of dissolved metal supply. All of this zone is physically reworked periodically, rapidly, so you can sustain the suboxic zone. And it's close to a steady supply of nutrients and dissolved metals, rivers, which is fueling marine diatom primary productivity. So what about biogenic silica burial? So there are different ways of estimating sedimentary biogenic silica storage, and they're traditionally done because it's very easy, easier than doing something like picking out individual diatoms or heavy liquid scintillation. They're traditionally done by alkaline leaches. And the one that's the most widely used is this one-step mild alkaline leach developed by Dave DeMaster, 1979. Now, this leach is really good for open ocean sediments or sediment that you can see has a significant fraction of diatom opal, but they don't work well for nearshore sediment because if you remember, that diatom frustral often forms a metal oxide coating. So there's another leach that was developed to estimate this reactive silica pool. first removed that metal oxide coating and then attacked the diatom silica frustral. So it's a mild acid plus a mild alkaline leach. And you can see that depending on what leach you use, you get an 8 to 10-fold difference in the amount of biogenic silica that you think is stored in your sediment. But even using that two-step leach, only a small portion of your altered diatoms is actually completely dissolved. So this is under a microscope after you've done those extractions. So really what we're talking about is biogenic silica contents that are at least double what you're measuring with this two-step leach. And you can keep using harsher leaches like sodium hydroxide, but then you're going to start to dissolve this background lithogenic terrestrial clay material, and it's going to become an indiscriminate leach between biogenic opal and a crystalline clay phase. So we need a new way to keep track of biogenic silica and this accounting balance. And one way to do that is through using this radioisotope of silicon, cosmogenic silicon-32. And it's produced in the atmosphere through cosmic ray spallation of argon-40. It has a half-life of about 140 years. As Alan mentioned, there's less than 1 kilogram on the Earth's surface at any time, though there are facilities that will produce silicon-32 if you're interested in doing silicon uptake studies and what have you. That silicon-32 is rained out, and when it's rained out onto the surface of the ocean, opal by silicifiers will take it up. Specific activity, this is disintegrations per minute. This measured specific activity of silicon-32 and opal is anywhere from 5 to 40 dpm per kilogram of SiO2. And once that opal, or once those silicifiers die, it becomes part of export production, or it's a major carrier of organic carbon as a ballast material, and they'll sink to margin silver of an ocean sediment. So what I've done is, or what has been done naturally, is that you have this naturally tagged biogenic opal pool, and you can use silicon-32 to track its fate through the water column and sediment. And additionally, you can directly calculate a burial flux, which is really important when you're going to take into the accounting balance in its budget and the budget of other constituents. Now, most of the silicon-32 measurements to date have been done in the 70s and early 80s, and that was pretty much it. So the specific activity of silicon-32 is inversely proportional to your dissolved silicon supply. This is a silicon-32 specific activity in sponges. A specific activity increases upwards, and this is your average DSI concentration. So you can see that as you increase your concentration, you decrease your silicon-32 specific activity. And this is the zone. I'm being a little generous here, but this is generally the zone of what you would expect your dissolved silicon concentrations to be in overlying water in these French Guiana mud belts. So you expect, this should be DPM, not DMP, you expect specific activities of 2 to 20 DPM per kilogram SiO2. So what did I do? So I have this biogenic opal pool. What I did was I developed this sequential extraction. And the first thing this sequential extraction targets is this unaltered biogenic opal pool, which I target with a mild leach. And then whatever a reactive silica is remaining can be targeted with a stronger alkaline leach like 4-normal sodium hydroxide. And 4-normal sodium hydroxide isn't strong enough to dissolve all of your silicates like your terrigenous clay material, but it should get all of your remaining reactive silica pool. So to reiterate, you have your whatever biogenic pool that's initially deposited to sediment. What I'm doing is I'm going to try and break by looking at silicon-32 activity into an unaltered biogenic opal pool and an altered biogenic opal pool. And if I do that, then I can talk about several things at the same time. I can test the accuracy of classic leaches. I can calculate how much biogenic silica content there is using silicon-32. I can differentiate between an unaltered and an altered phase. And because I'm using a chronometer with 140-year lifetime, I can start to constrain these rates of formation. So it's an independent way, in addition to these incubation methods, of how I can constrain these rates of formation. And the data come out as decay curves, where I'm actually measuring the daughter product of silicon-32, which is phosphorus-32. Has a half-life of 14 days. And you counted for 4 half-lives. And if you plot the data with counts per minute with reference to the half-life of phosphorus-32, if you get a straight line, then you know that the material that you're counting is silicon-32. So in French Guiana sediment, if there is no alteration of this biogenic opal pool, then all of my silicon-32 activity should be in this unaltered fraction that I initially extract. But there is no detectable activity in that fraction, even though you have quite high diatom counts in the sediment. Instead, all of my silicon-32 activity is in this altered, BSI altered pool in French Guiana sediment. So, because I described that, if you recall, this system can be described like a core, where the Amazon River mouth is the core top, and French Guiana is somewhere, in the middle of the core. So I can use an advection reaction model to calculate how much silicon-32 I need to add to sustain this activity. And this is about 7x to 700 kilometers downdrift of the starting point. I have C naught, I have C, which is your starting activity, and then your activity at some point down the road. And I have different velocities of anywhere from 1 to 3 kilometers. So the first thing to note is that the traditional leach only gets about 40 micromoles of silicon per gram. But the silicon-32 leach indicates that there's likely 2 orders of magnitude higher biogenic silica storage in these sediment. And I can calculate how much is being added to sustain this silicon-32 activity. It's not much. So this activity is supported by a small amount of BSI that's continuously added to a very large sediment transport system. And if I didn't have any addition of silicon-32, my decay curve should look like this. So whatever I sampled in French Guiana, if I didn't have any addition of marine biogenic silica, there should be no, I shouldn't have detected any activity in any of the pools. Now, one of my study sites was also in the Mississippi Delta, and these are some of the facies that you would associate with this region. And here, because it was right off the Bird's Foot Delta, you can use sediment accumulation rate and area to estimate the burial flux. Now, the other really interesting, so this is the subtropical end member. Now, in a temperate end member, the facies that is sustaining the suboxia is bioturbation. And these optodes are so cool. So these are 2-dimensional planar optodes. And this is showing pH evolution. You may not be able to see the numbers here, but this is 6.2 to 8.3 pH units. So these are worm burrows. You can see them here. And this is your pH scale. And you can see that 10 to 20, and they do extend up to 20 centimeters, 10 to 20 centimeters down core, this layer here, it is not accurately described by the steady state one-dimensional system. In fact, you have quite a lot of mass movement and organic carbon respiration and pH evolution through this top 10 to 20 centimeters. These are so cool. In fact, you can see with some of these brittle stars or burrows, they take material from up here and they deposit it up here. So you can see their fecal pellets too when they poop. If you've got CO2 sensors, you'll see like them shoving this really reactive organic carbon alongside their burrows that are just really rapidly respired. They're really cool. So these top 10 to 20 centimeters are rapidly reworked, even in temperate coastal margins. And this bioturbation, that's one of the mechanisms that maintains this condition, or these conditions that are conducive to authigenic clay formation. So if you put this all together, this light gray bar is the amount of biogenic silica storage you would estimate using the traditional leach. And you see that using silicon-32, the actual amount of biogenic silica that you're storing is 1 to 2 orders of magnitude higher. And so this is the Sider et al. 2014 distribution of biogenic opal in sediment. And they're all done using ODP cores. So they're not measuring anything along these coastal margins. And I put something over it, but generally that opal weight, for example, along the Amazon Guyana's coastal system is assumed to be something like 2 or less than 2 weight %. And instead you can see that using silicon-32, these tropical proximal coastal zones, subtropical, temperate, they have much higher biogenic opal weight than you would estimate through modeling. So by looking at the amount that's in that unaltered pool to the amount that's missing from silicon-32, I can get like a correction factor for how much biogenic opal you miss using a traditional leach. And you can see that in tropical systems, almost all of your opal pool is in an altered, diagenetically altered pool, whereas in subtropical and temperate estuaries, the fraction is a little bit lower. So generally, most silicon-32 is in the mineral pool in tropical deltaic sediments, and in temperate and subtropical, the correction factor that I used was about 50%. So you're missing half of your biogenic opal if you're using a traditional leach in these temperate and subtropical zones. So using that correction factor, I made an estimate. I can make an estimate for how much biogenic opal is being stored as authigenic clay in these sediments, or in these coastal zones, rather. And tropical deltas, like this dispersal system here. So this is a CWIFS image. You can see how productive that region is underneath my shading. So tropical deltaic systems stand out. This region right here and the Indo-Pacific archipelago, because they're so physically reworked and dynamic. And they have these extended zones of suboxia, plus all of this nutrient supply from rivers, that you just have this really high supply of fresh, organic marine material. And so let me talk a little bit about the coupling to the carbon system. So in the open ocean, we talked a little bit about this in the marine chem class. I don't know if any of you are here. Alan did talk about this, so you're coupled through primary production. And the diatom silicon to carbon ratio, molar ratio, is about 0.1 to 0.2. I know you all mostly talked about carbon, nitrogen, phosphorus, and oxygen. But this is the general coupling through primary production of silicon to carbon. Now, this is a coastal sample, and this is the Ross Sea. So typically, you assume that in the open ocean, after silicon and carbon are coupled through primary production, they become uncoupled as they settle through the water column, because you have higher rates of remineralization for organic carbon than you do for biogenic opal. So your burial ratio of silicon to carbon is, in the Ross Sea, is about 5, but generally it's much higher than 2. So that's a measure of how you can conceptualize how organic carbon and biogenic opal is behaving in the modern ocean. And then you can use that conceptual model to think about how it's behaved through time. And in continental margin settings or coastal margin settings, you assume that there's a much tighter coupling between silicon and carbon. So whatever is produced, you don't have as much time in the water column to respire all of that organic carbon. So these silicon to carbon burial ratios are assumed to be 0.4 to 1.2. And this is all based on this traditional leach. However, if you take independent measurements of organic carbon burial in these tropical and subtropical deltaic sediments, and now these new biogenic opal burial rates, you see that these numbers or these ratios actually fall more along this open ocean end member line. And in these tropical and subtropical deltaic systems, you have these differential remineralization pathways for silicon and carbon. You have almost near complete biogenic opal burial coupled with this rapid organic carbon incineration, some of which is potentially buried as an ophthalmogenic calcium carbonate. So burial ratios there in the proximal coastal zone of these systems are anywhere from 2.5 to 11 mole per mole, not the 0.4 to 1 mole per mole. And so even in the nearshore deposits, you have this uncoupling of silicon and organic carbon, silica and organic carbon. So depending on what element you're looking at, I'm not sure you can make a blanket assumption as we're finding out with so many other elements and so many other parts of our ocean about how it behaves in the nearshore versus in another location, or whether it's only dominated by trigonometric supply. I think you need to think about what it is that you're looking at specifically. So to put this into context, so a few decades ago, this is what the conceptual model of the marine silica cycle looked like. You didn't think about how much suspended particulate matter might be dissolving. You didn't think about marine silicate weathering or submarine groundwater discharge. And these are some of the big changes, I think, to the marine silica cycle. Marine SGD plays a big part in how much dissolved silica is entering the ocean. Sponges, the flux into been quantified. Hydrothermal vents are a little bit higher than we thought they were. And this is the contribution to the reverse weathering sink. So it's much higher than we thought before. And this is something from Chris's paper that's in revision. And regrettably, this is also a paper that's in revision. Regrettably, they were both submitted at the same time. So Traeger et al., this major synthesis that I hope will come out this year, may not have this number in it. So lots of work to be done. So again, to come back to this, the way that reverse weathering is modeled over Earth history, this study, for example, used this 1995 budget. And their rate constraints are based on clay formation with no solid substrates in lab conditions. And here, this is the present day, and this is back through time. Silicon to alkalinity consumption ratios are based on pedogenic clay formation, and they make other assumptions about weathering congruency, about how silicon and carbon are coupled. So even though some parts of this may be wrong, I think the correct. I think the conceptualization of how reverse weathering and carbon are coupled, that this is a really wide open field of the actual reactions that are taking place. Now, there are only 3 reactions of, I'm going to skip this part. There are only 3 reactions of orthogenic clay formation that have been published. And so let me just bring this back. So the silicon to alkalinity ratios here, they assume a 1 to 4 molar ratio of, excuse me, yes, 1 to 4 molar ratio of silicon to alkalinity consumption. But you can see that with clay formation, I just want to point out the dissolved silicon to alkalinity consumption ratio here. So instead of, roughly 2 moles per mole of consumption, in any of these only 3 balanced budgets or reactions of orthogenic clay formation, the alkalinity to silicon, dissolved silicon consumption, a molar ratio is actually about 0.1 to 0.3, not 2. And you can use that to make some estimates of how much magnesium you think is buried as a reverse weathering product and how much potassium, depending on how much iron you have. Iron seems to be a really critical player in how much the type of clay that you're forming. So in the 1995 budget, most opal burial was thought to be happening in the open ocean. And I think we've changed and have quite a bit of evidence that shows that you have quite a lot of biogenic opal burial that's buried in continental margins here. So I'm going to wrap up. Tropical sediments, most of your silicon-32 activity is in the mineral pool. So that means that most of your biogenic opal that you buried has undergone diagenetic alteration. And in temperate and subtropical estuaries or zones, I'm assuming a conservative number that only 50% of biogenic opal undergoes diagenetic alteration. There's about 4.5 to 5 teramoles buried as an orthogenic clay in continental margins, and only about 3.5 that's buried as a opal phase. Silicon-32 is a really powerful tool, and we need more data. So maybe we can get geotraces on that. That would be great. The conversion to an orthogenic clay is rapid. I'm saying it's within a few years to be generous, but really you can see it forming within a few months. And in tropical sediments, your opal substrate is what's going to limit your magnitude of formation, whereas in temperate settings, it seems like it's how much dissolved iron or aluminum is available that limits the reactions. And all of these findings are consistent and complementary with these prior lines of evidence that I showed earlier. So this is all a mouthful. Instead, maybe you can just remember crumb as you're ruminating. Reverse weathering reactions have exert critical controls on the carbon cycle. Rapid rates of formation, and these seem to be occurring everywhere in continental margins. And now there's some emerging evidence that it's happening in open ocean settings as well. The magnitude is large enough to be able to close the budgets of other elements and constituents. And with that, I will take questions. This is the Amazon River plume right here, which I thought was a really cool image. And with that, I will take questions. Thanks for your attention.
Okay, thanks, Shaily. Everybody can clap at home. So we were right at 12 o'clock, so I understand if people need to leave, but if you can stick around, why don't we take a few minutes for questions? And you can raise your hand or just go ahead and unmute yourself any way you want to ask a question. I have 2 questions to start out.
Sure.
One is, yeah, the mobile muds. It's really cool to think about that as a paleo record of what's coming out of the river. And so you had some assumptions that it was they move at a speed of about 1 kilometer per year. Is that right?
1 to 3 kilometers per year. Yes.
And is that like, do they physically watch them with?
Yes. So these were They're now physically watching them with pictures. So this is a lot of information that is now coming out of a lot of French working groups, like the BioMango group. But that 1 to 3 kilometers per year, this is like a hydraulic study that was done a few decades ago, and has been reconfirmed throughout the years for geological oceanographers and remote sensing folks who are working in that region, mostly through Infomar.
And my other question was, do you know how much seawater you would need to measure the silicon-32?
In geosets, they calculated that they pumped, a rough estimate is about 300 to 400 cubic meters of seawater. But that's not what, yeah. But that's not what they actually did. I think they just deployed these. So the way that silicon-32 is measured, it's the same way that beryllium-7 and beryllium-10 are measured. So you have these iron oxide coated fibers. And with beryllium-10, you actually need to know like this uptake record because it's a non-destructive method for measuring its activity. It's like you just make it into a plug and put it in a gamma detector, right? So you actually need to know how much seawater you're pumping through that filter. But I think with geospecs and with silicon-32, they just dumped it over the side, and they had a bag protecting it, and they kind of like trailed it, and they brought it back up. And because the way you measure silicon-32 is that you completely dissolve your iron oxide fiber, you can then take a subsample to measure how much silica you have. And so they just calculated based on how much silica they collected and the concentration of seawater at that depth. They calculated how much they were likely sampling, the volume. So I don't think you actually would need to filter water through it. You could, because it's a destructive technique, you can get your specific activities in a different way. Does that make sense?
Yeah. Do we have any other questions?
Yeah, I'll ask one. I suppose you know my question, which is simply, all right, which trace elements should we be looking at in this?
So my answer would be that you should look for anything that is hosted in a silicate mineral that gets weathered, has the chance of being reprecipitated into an authigenic clay. So the ones that have gained some attention recently are lithium and germanium specifically, but also rare earth elements. And we've had a little bit of discussion about maybe other elements like barium could also be maybe be incorporated into authigenic clays. One really critical micronutrient that seems to be sequestered into green glauconite type clays is iron. So it's unclear what the magnitude of the iron flux is into authigenic clays. And because it won't be sequestered as a pyrite, you don't really have that same chance of it being dissolved and not being buried. So that's an interesting question right there. There's some papers by Balderman et al. 2015, a German group that's looked into this a little bit. So those I'm really curious about that, the iron sink potentially, and lithium and germanium.
Okay. If there's nothing else, we can thank Shaily again. And yeah, she's a postdoc in our marine science department. I know we're not all seeing each other in the hallways right now, but you feel free to reach out to her if you have any more questions. So thanks, Shaily.
Thank you. Bye.